There are moments in science when a line of data forces a civilization to pause. In 2023, one of those moments arrived quietly, encoded in infrared light from a planet 40 light-years away. The James Webb Space Telescope turned its mirror toward TRAPPIST-1e, an Earth-sized world orbiting a faint red dwarf star. The observation was not symbolic, it was surgical. Using the Near Infrared Spectrograph, Webb measured how starlight changed as the planet passed in front of its star. The goal was direct and uncompromising: determine whether this rocky world possesses an atmosphere. What came back was not an image, it was a spectrum, variations measured in parts per million, shifts so small that they approach the precision limits of modern astrophysics. Yet inside those shifts was a result with enormous consequence. Webb ruled out a thick hydrogen-dominated atmosphere with high statistical confidence. The planet is not a miniature gas giant. It is not wrapped in the kind of primordial envelope many small worlds retain. That single exclusion reshaped its identity. TRAPPIST-1e is a compact, evolved terrestrial planet. But the deeper revelation was not certainty. It was division. After correcting for stellar interference, dark star spots, bright faculae, fluctuations in brightness, two physically consistent realities remained. In one, the planet is bare rock, its early atmosphere stripped away by intense radiation during the star's violent youth, a surface exposed to vacuum, a world that failed the test of survival. In the other it endured, a thin secondary atmosphere, likely nitrogen-dominated, perhaps mixed with carbon dioxide, clings to the planet. Not thick, not lush, but sufficient to alter surface temperature, pressure, and the stability of liquid water. Both interpretations fit within the current uncertainty margins. Neither yet crosses the 3 sigma threshold required for confirmation. The data does not choose between them, and that is what makes this moment extraordinary. For the first time in history, humanity is no longer asking whether we can detect Earth-sized planets. We are asking whether one of them still carries air. The distinction between a dead world and a potentially habitable one now depends on spectral lines measured across 40 light-years of space. Red dwarf stars like this dominate our galaxy. If planets such as TRAPPIST-1e can retain atmospheres, then habitable conditions may be common. If they cannot, then many of the galaxy's Earth-sized worlds are silent stone. Webb did not deliver an answer, it delivered a boundary. To understand why this faint star became the focus of planetary science, and how we reach the point where 2 entire planetary fates hinge on subtle infrared signatures, we must go back to the beginning of the system itself. In February 2017, a press conference from NASA carried an unusual weight. Astronomers were not announcing a single exoplanet. They were unveiling an entire system. 7 Earth-sized worlds orbiting a star barely larger than Jupiter. It was a configuration no model had confidently predicted. The discovery centered on TRAPPIST-1, an ultra-cool red dwarf located 40 light-years away in the constellation Aquarius. Though the star itself had been catalogued in 1999, its planetary architecture remained hidden until an international collaboration led by Belgian astronomer Michael Gillen began systematic observations with the TRAPPIST-South telescope in Chile and its northern counterpart in Morocco. Using transit photometry, the team measured periodic dips in the star's brightness, decreases of less than 1%. Each dip signaled a planet crossing the stellar disk. What began as 3 candidate worlds rapidly expanded. Follow-up observations by NASA's Spitzer Space Telescope refined orbital periods, masses, and resonant interactions. By early 2017, 7 planets were confirmed. The implications were immediate. All 7 planets orbit closer to their star than Mercury orbits the Sun. Their orbital periods range from roughly 1.5 to 18 Earth days. Yet several lie within what astrophysicists define as the habitable zone, the narrow region where surface temperatures could allow liquid water, given sufficient atmospheric pressure. TRAPPIST-1e emerged as the most compelling. Its radius is nearly identical to Earth's. Its density indicates a predominantly rocky composition. It receives approximately 23% of the stellar energy Earth receives from the Sun. placing it near the centre of the system's temperate region. But the architecture of the system raised profound questions. Red dwarfs are volatile in their youth. High-energy radiation and stellar winds can erode planetary atmospheres over millions of years. If these planets formed early, they would have endured prolonged exposure to flares capable of stripping volatile gases into space. Could such tightly packed terrestrial worlds retain atmospheres at all? Planetary formation models struggled to explain how 7 rocky bodies assembled in stable orbital resonance so close to a low-mass star. The system challenged assumptions about disk chemistry, migration, and long-term climate stability. For the first time, astronomers had a natural laboratory, multiple Earth-sized planets orbiting the same star under slightly different radiation conditions. Comparative habitability became measurable rather than theoretical. The 2017 announcement did more than expand the exoplanet catalogue. It shifted the focus of planetary science from detection to characterization. If even one of these worlds retained a stable atmosphere, the implications for galactic habitability would be profound. But confirming that required technology beyond the capabilities of Spitzer or Hubble. To answer whether TRAPPIST-1e endured, whether it remained a barren remnant or evolved into something more stable, a new observatory would be needed, and that observatory was still waiting on the launch pad. On December 25, 2021, the most powerful space observatory ever built left Earth aboard an Ariane 5 rocket. The James Webb Space Telescope was not designed merely to discover planets, it was built to dissect them. By mid-2023, Webb turned its 6.5-metre mirror toward TRAPPIST-1e. For the first time, an Earth-sized planet in the habitable zone of another star would be examined for atmospheric composition with unprecedented infrared precision. The method was exacting. As TRAPPIST-1e crossed in front of its star, a small fraction of starlight filtered through any atmosphere surrounding the planet. Molecules absorb specific wavelengths of light. Hydrogen, carbon dioxide, methane, nitrogen, each leaves a measurable spectral imprint. Webb's Near Infrared Spectrograph, NIR spec, recorded these changes at sensitivities approaching tens of parts per million. The stakes were clear. If hydrogen absorption lines appeared strongly in the spectrum, the planet would likely be wrapped in a thick primordial envelope, hostile to surface life as we understand it. If no atmosphere were present, the spectrum would remain largely flat, dominated only by stellar contamination. But if subtle features from heavier molecules emerged, it would suggest a secondary atmosphere, one built through geological processes. Yet the experiment faced a formidable obstacle. TRAPPIST-1 is not a stable sun-like star. It is an ultra-cool red dwarf prone to variability. Star spots, cooler regions on the stellar surface distort brightness. Brighter faculae alter spectral balance. Flares inject bursts of high-energy radiation. Each effect can mimic or conceal planetary signals. Separating planetary atmosphere from stellar noise required complex modelling and repeated transit observations. Multiple passes, each lasting less than an hour, were stacked and analysed. Statistical corrections were applied to isolate planetary contributions from stellar interference. When the results emerged, the first conclusion was decisive. Hydrogen-dominated atmospheric models were rejected with high statistical confidence. The expected absorption signatures were absent. That exclusion alone marked a breakthrough. For the first time, a telescope had ruled out a thick primordial atmosphere around an Earth-sized exoplanet 40 light-years away. But beyond that boundary, the data entered uncertain territory. After corrections, the remaining spectrum could be interpreted in 2 ways. Either TRAPPIST-1e is nearly airless, its atmosphere long stripped by stellar radiation, or it retains a thin secondary atmosphere composed primarily of heavier gases. Neither scenario yet exceeds the 3 sigma threshold required for confirmation. The difference lies within the margin of instrumental and stellar modelling uncertainty. Webb did not reveal a definitive atmospheric fingerprint. It revealed the edge of detectability itself. To understand what those 2 possibilities mean for climate stability and the survival of liquid water, we must now examine the physics governing such a world. Imagine looking at Earth from 40 light-years away. You cannot see oceans. You cannot see continents. All you can measure is how sunlight changes as it passes through our air. From that faint distortion, you would know our planet is alive, with atmosphere. In 2023, scientists attempted that same experiment on TRAPPIST-1e. After months of analysis using data from the James Webb Space Telescope, one conclusion became clear. If TRAPPIST-1e were wrapped in a thick blanket of hydrogen, the light, puffy gas that surrounds many small exoplanets, Webb would have seen it immediately. Hydrogen leaves bold, unmistakable fingerprints in infrared light. Those fingerprints were not there. This absence may sound simple. It is not. A hydrogen atmosphere acts like insulation around a planet. It traps heat, inflates the planet's size, and often prevents a solid surface from existing in familiar conditions. Many worlds discovered in the last decade turned out to be rocky cores buried beneath deep hydrogen layers. TRAPPIST-1e is different. The data rules out that kind of thick gaseous envelope with high statistical confidence. In practical terms, this planet is not a small gas giant. It is a compact, rocky world. If you could stand on it, you would stand on solid ground. But that clarity opens a deeper mystery. Young red dwarf stars are violent. They flare intensely and emit radiation capable of peeling away a planet's atmosphere molecule by molecule. Hydrogen, being the lightest gas, escapes first. Over time, a planet can be stripped bare. So the question becomes unavoidable. Did TRAPPIST-1e lose everything, or did it rebuild? On Earth, our current atmosphere is not the one we started with. Early hydrogen was lost billions of years ago. Volcanic eruptions released nitrogen and carbon dioxide. Chemical reactions locked and recycled gases. Slowly, a secondary atmosphere formed. The same process could occur on TRAPPIST-1e, but only if the planet still has internal heat, geological activity, and gravity strong enough to hold heavier gases. Webb's discovery does not confirm a breathable sky. It confirms something more fundamental. This planet crossed a threshold. It evolved. It either survived the storm and forged a new atmospheric layer, or it stands exposed to space, a rocky surface under an unfiltered star. The difference between those two worlds is measured in subtle variations of infrared light, differences so small they approach the limits of modern instruments. And within that narrow margin lies the line between climate stability and cosmic silence. To understand which reality is more likely, we now have to examine the delicate statistical boundary that still divides the data. In 2023, after ruling out a thick hydrogen blanket, scientists expected the next answer to be clearer. Instead, the data placed TRAPPIST-1e on a knife's edge. When researchers processed the James Webb Space Telescope observations, correcting for stellar flickers, dark spots, and instrument noise, they found that two very different versions of the planet fit the measurements almost equally well. In the first version, the planet is exposed rock. Picture a world where the sky does not exist. No clouds, no air to carry sound. On the side facing its star, heat builds without moderation. On the opposite side, darkness never lifts. Without an atmosphere to move warmth around the globe, temperatures could swing hundreds of degrees between hemispheres. Any water would either boil away into space or freeze permanently in shadow. In the second version, the planet survived, not with a thick, crushing atmosphere, not with blue skies and oceans, but with something thinner, a layer of heavier gases like nitrogen. Even a modest atmosphere can act like a planetary thermostat. It spreads heat from day to night. It creates pressure at the surface. It allows liquid water, under the right conditions, to exist instead of instantly evaporating. The astonishing part is how small the difference is in the data. Webb is measuring changes in starlight, so slight they are comparable to detecting a single breath, altering the brightness of a lighthouse seen from thousands of kilometers away. The remaining spectral variations fall within margins that do not yet cross the 3 sigma confidence level required for confirmation. In simple terms, the evidence is not strong enough to declare a clear winner. But this uncertainty is not ignorance. It is precision at the frontier of human capability. For decades, we asked whether Earth-sized planets even existed around small stars. Now we are debating whether one of them still holds air, based purely on how its star's light bends through space. The implications stretch far beyond this single world. Red dwarf stars make up most of the Milky Way. If their planets commonly lose atmospheres and remain bare rock, then countless Earth-sized worlds are silent and sterile. But if TRAPPIST-1e rebuilt even a thin atmosphere after enduring intense stellar radiation, it suggests something profound. It suggests resilience, and resilience, at a galactic scale, changes everything. To decide which version of this world is physically plausible, we must now examine the environment it inhabits, its gravity, radiation history, tidal locking, and internal heat. Because survival in space is not a matter of hope, it is a matter of physics. If TRAPPIST-1e has survived with an atmosphere, it has done so under conditions far harsher than Earth ever faced. To understand whether survival is realistic, scientists in 2023 began modelling the planet's physical environment using updated Webb constraints and long-term stellar evolution data. The question was no longer simply what the telescope saw. It was whether the laws of physics allow this world to hold air at all. TRAPPIST-1e orbits its star once every 6 Earth days. That distance is so small the entire system would fit inside Mercury's orbit. At such proximity, tidal forces likely locked the planet into synchronous rotation. One hemisphere faces the star continuously, the other remains in permanent night. Without an atmosphere, this configuration creates extreme imbalance. The day side absorbs steady radiation. The night side radiates heat into space with no replenishment. Climate models show temperature contrast could exceed hundreds of degrees Celsius under airless conditions. But gravity matters. TRAPPIST-1e's mass and radius indicate a surface gravity comparable to Earth's. That is critical. Gravity determines how tightly a planet can hold onto heavier gases. Nitrogen and carbon dioxide move far more slowly than hydrogen. If released through volcanic outgassing, they are significantly harder to strip away. Radiation history complicates the picture. Red dwarfs like TRAPPIST once spend their early lives in prolonged active phases. Ultraviolet and X-ray radiation can drive atmospheric escape, especially during the first billion years. Models suggest that lightweight gases would have been removed efficiently. However, once stellar activity declines, as it does over time, escape rates drop dramatically. If TRAPPIST-1e retained internal heat, volcanic processes could replenish its atmosphere after the most violent stellar period ended. Even a relatively thin atmospheric layer, perhaps a fraction of Earth's surface pressure, could redistribute heat from day to night through global circulation. Computer simulations show that with sufficient surface pressure, wind patterns could transport warmth into the dark hemisphere, preventing total atmospheric collapse through condensation or freeze-out. This is the central discovery emerging from environmental modelling. Survival is physically plausible, not guaranteed, not proven, but consistent with gravity, chemistry, and stellar evolution constraints. The difference between a frozen rock and a climate-stabilized world may depend on internal geological activity, a factor Webb cannot directly observe. To place this possibility in context, we must now step back and examine the larger population of red dwarf planets across the galaxy. Because if TRAPPIST-1e can endure, it may not be alone. TRAPPIST-1e is not important because it is unique. It is important because it may be typical. Red dwarf stars make up nearly 70% of all stars in the Milky Way. They are smaller and dimmer than our Sun, but they dominate the galaxy in sheer numbers. For decades, many scientists believe planets orbiting these stars faced overwhelming odds against long-term survival. Their habitable zones sit extremely close to the star, forcing planets into tight orbits that complete in just a few days. During a red dwarf's early life, intense radiation and stellar flares can blast nearby planets with high-energy particles capable of stripping atmospheres into space. The prevailing assumption was straightforward. Most of these worlds would end up bare. Webb's 2023 observations of TRAPPIST-1e introduced a complication to that narrative. The telescope did not confirm an atmosphere. but it demonstrated that complete atmospheric destruction is not the only outcome consistent with the data. Survival remains physically plausible. That possibility carries enormous weight. Planet surveys from missions like Kepler have already shown that small rocky planets are common around red dwarfs. What remained uncertain was whether they could keep the thin layer of gas necessary to stabilize surface temperatures. The difference may come down to something surprisingly delicate. A relatively thin atmosphere, perhaps far less dense than Earth's, can still circulate heat, create surface pressure, and prevent water from instantly freezing or boiling away. Remove that layer, and the same planet becomes a silent, frozen, or overheated rock. The astonishing realization is that the boundary between those two fates may be narrow. TRAPPIST-1e sits precisely at that boundary. Its gravity appears strong enough to hold heavier gases like nitrogen. Its radiation history suggests intense early loss, followed by a calmer stellar phase. Geological activity, if present, could replenish an atmosphere after the worst radiation subsided. This reframes the galactic equation. When scientists estimate how many worlds in the Milky Way might support life, one key variable is how many planets remain habitable long enough for biology to emerge. Red dwarfs were once considered poor candidates, yet the data now suggests resilience cannot be ruled out. Even a modest survival rate among red dwarf planets would multiply the number of potentially stable worlds by billions. Caution remains essential. The spectral data from TRAPPIST-1e has not yet crossed the 3 sigma confidence threshold needed to confirm a nitrogen atmosphere. The conclusion is not final, but the shift in perspective is already significant. A galaxy once thought to be filled largely with sterile rock may instead host vast numbers of worlds, balanced delicately between collapse and stability. To understand why earlier models may have underestimated this resilience, we now turn to the counterintuitive physics emerging from this remarkable system. For years, planetary models predicted that worlds orbiting red dwarfs would struggle to survive. The logic seemed solid. Young red dwarfs remain active far longer than sun-like stars. They emit intense ultraviolet and X-ray radiation. Their stellar winds are persistent. Any nearby planet, especially one orbiting every 6 days like TRAPPIST-1e, should have had its atmosphere stripped away early and permanently. Yet, in 2023, as climate simulations were updated using constraints from the James Webb Space Telescope observations, a more complicated picture emerged. The central discovery was not a direct detection, but a realization. Atmospheric survival under these conditions is not only possible, it may be dynamically stable. The key lies in counterintuitive physics. Tidal locking, once considered a fatal flaw, does not automatically destroy habitability. Early models assumed that permanent night would cause atmospheric gases to freeze out and collapse onto the dark hemisphere. But advanced, three-dimensional climate simulations show that even a relatively thin nitrogen-rich atmosphere can circulate heat efficiently. High-altitude winds can transport thermal energy from the day side to the night side, preventing total freeze-out. Gravity adds another layer of resilience. TRAPPIST-1e's mass suggests surface gravity comparable to Earth's. That gravity significantly slows the escape of heavier molecules. While hydrogen would be lost rapidly during the star's active youth, nitrogen and carbon dioxide are far more difficult to remove. Once the star settles into a quieter phase, as red dwarfs eventually do, atmospheric erosion rates decline sharply. Another surprise involves time. Red dwarfs burn slowly and can remain stable for trillions of years. Even if early radiation stripped an atmosphere, geological processes could replenish gases long after stellar activity decreases. In other words, habitability around red dwarfs may be delayed rather than destroyed. This reframes earlier pessimism. Instead of asking whether planets survive early violence, scientists now ask whether they can recover from it. The answer, based on updated modelling in 2023 and 2024, appears physically plausible for worlds with sufficient gravity and internal heat. The stakes are profound. If TRAPPIST-1e demonstrates that tidal locking and early radiation are not automatic death sentences, then planetary evolution around red dwarfs may follow pathways more diverse than once assumed. Stability may emerge not despite harsh beginnings, but after them. Yet this remains a theoretical reconciliation. Webb's spectral data has not yet provided direct molecular confirmation above the 3 sigma confidence threshold. The physics allows survival, but the atmosphere itself remains observationally unresolved. To understand how unusual or common such resilience may be, we must compare TRAPPIST-1e with other known rocky exoplanets and determine whether it represents an exception or the beginning of a pattern. That broader comparison brings us to the next stage of this unfolding investigation. By 2024, TRAPPIST-1e was no longer being examined in isolation. The central discovery that a rocky planet orbiting a red dwarf could plausibly retain or rebuild a secondary atmosphere demanded comparison. Was this system an anomaly, or the first clear example of a broader pattern emerging in exoplanet science? Over the past decade, missions such as Kepler and TESS revealed that small rocky planets are common throughout the galaxy. Many orbit red dwarf stars. Statistical analyses indicate that a significant fraction of these stars host at least one Earth-sized planet within their temperate zone. The question was never abundance, it was endurance. Prior to Webb's launch in December 2021, atmospheric characterization of Earth-sized exoplanets remained largely theoretical. Larger sub-Neptunes displayed thick hydrogen envelopes. Smaller rocky worlds were too faint for detailed spectroscopy. TRAPPIST-1e became the first terrestrial-scale test case where hydrogen was decisively ruled out. That result reframed comparisons. Several rocky exoplanets around red dwarfs show densities consistent with solid surfaces. Some orbit even closer to their stars than TRAPPIST-1e. Yet without spectral constraints, their atmospheric states remain unknown. Webb's findings introduced a new category: evolved, compact, terrestrial worlds around low-mass stars that are not mini-gas giants. The implications are statistical rather than dramatic. If TRAPPIST-1e proves to retain a nitrogen-rich atmosphere, it would suggest that secondary atmospheres can persist under red dwarf conditions. If it is bare, it sets measurable limits on atmospheric survival timescales. Either outcome sharpens models for dozens of similar systems already catalogued. In 2023 and 2024, exoplanet climate researchers began integrating Webb constraints into broader population models. Instead of assuming atmospheric collapse for tidally locked red dwarf planets, new simulations consider pressure thresholds, volatile inventories, and long-term stellar evolution. The shift is subtle but significant. TRAPPIST-1e now functions as a calibration point. Its orbital period of 6 days, Earth-like gravity, and moderate stellar flux provide a benchmark for comparing other compact systems. Each additional observation will test whether its resilience or its vulnerability reflects a common evolutionary pathway. The stakes extend beyond individual worlds. When astronomers estimate the number of potentially habitable planets in the Milky Way, they rely on statistical distributions. One well-characterized terrestrial planet can refine those distributions dramatically. A single confirmed nitrogen atmosphere around a red dwarf planet would alter galactic habitability estimates by orders of magnitude. Yet caution remains essential. Current spectral data still falls below the 3 sigma confidence threshold required for definitive atmospheric confirmation. The comparison phase has begun, but the conclusion is not final. What is clear is that TRAPPIST-1e marks a transition, from discovering planets to measuring their physical realities. To grasp the full meaning of that transition, we must step back and consider what this moment represents in the broader arc of human exploration. Because beyond the data lies a deeper shift in perspective. Part 10, the line between silence and air. In 2023, humanity reached a threshold that previous generations could only imagine. For the first time, a space telescope measured the atmospheric possibilities of an Earth-sized planet orbiting within the habitable zone of another star. Not a gas giant, not a distant theoretical world, a rocky planet, comparable in size and gravity to Earth, examined through the precision of infrared spectroscopy by the James Webb Space Telescope. The central discovery was not the detection of life, it was the narrowing of reality. TRAPPIST-1e is either a barren world stripped of air long ago, or a resilient planet that rebuilt a thin secondary atmosphere after surviving intense stellar radiation. The hydrogen envelope is gone, ruled out with high confidence. What remains is a subtle spectral boundary between absence and endurance, a difference measured in parts per million of starlight. The stakes extend beyond curiosity. Red dwarf stars dominate the Milky Way. Their planets represent the majority of rocky worlds in our galaxy. Whether those worlds can retain atmospheres determines how many environments might sustain stable climates over billions of years. The outcome influences the estimated abundance of habitable planets, a key parameter in the Drake equation and in humanity's broader understanding of its place in the cosmos. Webb's data has not yet crossed the 3 sigma confidence threshold required to confirm a nitrogen-rich atmosphere. Scientific caution remains essential. The distinction between a silent rock and a climate-bearing world rests on additional observations, refined stellar models, and future transit measurements. Yet something irreversible has occurred. The search for life beyond Earth has shifted from speculation to measurement. We are no longer limited to counting distant planets. We are beginning to analyze their air. A generation ago, detecting an Earth-sized planet around another star was considered ambitious. Today, we are debating the composition of its atmosphere 40 light-years away. TRAPPIST-1e stands at the edge of that transformation. Whether it proves barren or resilient, it marks the moment when planetary science crossed from discovery into diagnosis. It represents a turning point, where technology allowed us to test survival against physics, radiation, gravity, and time. In the coming years, additional observations will refine the spectrum. Noise will diminish. Statistical certainty will increase. The ambiguity will collapse into clarity. When that happens, the answer will not simply describe one distant world. It will tell us whether planets under red suns are mostly silent stone, or whether, across the galaxy, thin layers of unseen air may be more common than we ever dared to calculate.